So before we go into the details of what tracking by assignment is, let's just say tracking in general. Tracking means that we have a couple of particles or of targets that we want to follow. So we want to trace the identity of some targets across time. And early applications were of a military nature, but this was also required for all of the space program, yeah, so to launch rockets with satellites and so on. Tracking was required. And it is sometimes said that the Kalman filter, one particular kind of tracking algorithm, only made the American space program possible in the first place. Now, for such tracking problems, there are three schools of thought. Namely, there is one view of the problem which is in terms of a space-time segmentation. And in some ways, if the temporal resolution is high enough, I think this is perhaps even the most elegant way of addressing the problem. So I'm giving you a 1D example here. So let's say one particle moving one particle moving would be one sausage or one tube in space-time. And if we have data in which occlusions can occur, so let's say I have a stationary particle here, and then one which is moving, another one which is moving, I may obtain something like this. But I will say that we want to trace the identity of objects. If we are lucky, the objects will have distinguishing features such as color or so, which will help us figuring out after such an occlusion event which is which. So if there was a crossover or if they've been colliding the two particles. This only works if the temporal resolution is very high. So, if I subsample this strongly, let's say I have one measurement here, and then the next measurement is down there in time, then this notion of having sausages in space-time no longer works. What we need is really very good overlap of the targets in adjacent time steps. So if I take as one criterion, if the method can handle large displacements, then I have to give the space-time segmentation a minus. There's another class of methods that excel at such data with low temporal resolution. Those are the state space methods, and the most famous representative from that family is the Kalman filter. This is a directed graphical model. We have only talked about undirected probabilistic graphical models in this course. If you want to learn more about the directed graphical models, I will give a short course just in the week before the next semester starts. We have some variables that are observed. So these are the detections, and then some hidden state that evolves in a Markovian fashion over time. And this allows us to deal also with large displacements by creating a rich representation for the internal state. So I can, for example, if I know that I'm tracking a single particle, then I can say what is the velocity of this particle, or what is its initial position, and so on. And I can make, if I know the at least approximate equations that govern the dynamics of a system, then I can use these to propagate the expected internal state of the system. So we can conveniently represent the internal state in such state space models. This is less easy with space-time segmentation. And finally, the third major class are tracking by assignment or data association methods. And we will talk about these at length today. So let's say I have some detections at time t and some detections at time t plus 1. And I'm then reasoning about which assignment of particles is the most likely. This can also handle large displacements. It cannot easily represent an internal state. However, it is much easier to handle an unknown number of particles using this approach. That's harder for state space models. Space-time segmentation can also handle an unknown number of particles. Also, if you're in a situation where your particles can divide, so dividing targets, that is particularly important in certain biological applications. The first approach can handle this. State space methods, no. Tracking by assignment, yes. And these latter two methods, they treat the detection and the tracking problem separately. And really, it's more interesting to do that jointly, or more elegant. So a joint detection or segmentation and tracking is something that the first class of method does inherently, and these two do not. Now, when I put pluses and minuses here, this is a bit of a simplification. So you can always modify these methods so as to turn a minus into a tentative plus or into a real plus. But I'm talking here about the most straightforward implementations. So the interesting thing about this table is that there is, no single method that has all pluses. So each view or each of these schools has its own advantages and problems. However, in our own work, we deal a lot with dividing targets, and the data resolution is low. So if I want things that are that can divide, and if I want to allow for large displacement between time frames, then you see I have a plus here and I have a plus there. This is why we went for tracking by assignment methods. And I want to explain in some more detail how this works. This family of techniques has at least two names: tracking by assignment and data association, and I think there are others. As I said, it separates the detection and the tracking step. So first, candidates for targets are detected in each time step. And then secondly, one tries to establish the correct correspondences between such target candidates. And I will, in the following, consider a simplified scenario where I make a couple of assumptions that are not necessary, but I don't want to make things too complicated. So in my simplification, I will assume that we have perfect detection. What I mean by that is that we have no false positives and no false negatives. So we detect all particles, and all the particles that we detect are really particles and not something that we have fantasized into the data. I will also assume for the moment that there is no appearances of new particles, no disappearances of any particles over time, and I will assume that we don't need to deal with divisions, and I will assume that we're happy to consider only pairs of time steps. So really one should solve the tracking problem by looking at all of the data from the very beginning to the very end, but here we just look at pairs of time steps. Let me give an example. So let's say I have a time step t and a time step t+1, and that I have seen a few objects. Let's say there was one object here, and one there, and one down there. And now I can consider a number of possible associations. I could say this one from the first time step corresponds to that one, or I could assume that it corresponds to this one. And if I looked at only this particle here, the first one on the left-hand side, it's probably not clear what is the correct answer. Or maybe I would even vote for this one here, because if I interpret the second dimension here as space, then I need to assume less of a motion if I associate the particle here with that one on the right-hand side. But for now, I don't know. So the second particle, I assume, could be this one, or it could be that one, or it could be that one. And the third particle, that seems a plausible assumption, and I'm not considering, let's say, the one corresponding to the dashed line here, simply because it's too far away. So I'm using some kind of maximum distance heuristic in creating these possible assignments. If I didn't do that, I should connect every target from the first step with every target from the second step. So I would get a similar picture, but with a few more lines in there. So this was my step number one. Well, first I had detected all targets. And secondly, I have established all possible associations. And I've put all in quotation marks because I can use some cutoff criterion, as I've just argued, to simplify things. The simplification is not really necessary if I have 3 targets at t and 3 targets at t+1, but if you have, let's say, thousands of cells that you want to track, this becomes a necessity. Let me show an example. So here's a 2D tracking example. And well, these were just 3 time steps and only a few cells moving. But if you have thousands, or then you don't want to connect every detection in one time step with every detection in the next time step. Okay, now since we've become experts in graphical models, I will turn this into a graphical model. I will associate a random variable, which I indicate with a circle, with each of these associations. So I'm drawing a circle I'm drawing one circle on top of each of these lines. And I will say that these are unary, or these are random variables which can either be 0 or 1, where 1 means I believe that this is the correct association, and 0 means I do not believe this is a true association. So I associate a binary random variable. Now I have a sentence with 2 associations. Give me a synonym for associate. Assign, thank you. Assign a binary random variable to each association. Okay, now if I just look at each assignment by itself, I can certainly have an opinion if that is a good or a bad assignment, and I can encode this opinion in terms of a unary factor. So I'm drawing these small black boxes here to say that in a factor graph, these are my unary factors, or these are, if we talk about energies, these are my potentials, which depend on the state of just a single random variable. And these unary factors have an opinion about if an association is good or bad. So, for example, a good association would be one where particle does not have to move very far, or a good association would be one that links two particles which are of similar size, or let me more generally say of similar appearance. So to stress this point, let's assume that one of these detections was much, much bigger than the other ones. And if I take size into account, then I would believe that this one here is more likely to correspond to that one there than this one here, which would have a big size difference. So I can, in the next step, establish unary factors that I've drawn as black boxes based on. And now this is your chance to inject what domain knowledge you have. So for example, if I believe that things should not move around too much between two time steps, then I would say that the proximity of the two associated detections, proximity in space, would be a good feature here. Or I could consider the similarity in size, or similarity in shape, however you define that, or I could say similarity in brightness. So you can find different ways of summarizing the appearance and then measuring the difference of these appearances. And at this point, we have these random variables, we have the associated factors. So at this point, we could already formulate an energy function, or we could already, given this energy function, come to a decision. And this would be a decision which would be independent for each of the associations. So, for example, I could decide that I like this association here. I switch it on, and I could decide that I switch this one on also. However, I would have the problem now that both associations being on would mean that somehow both of these detections in the first step would correspond to the single detection in the second step. And in my simplifying assumption, I was saying that the detections are perfect. So no false positives, no false negatives. Perhaps I should have extended this list and said there are also no false mergers, etc. So the assignment that I've just drawn was an impossible one because I had two particles assigned to the same one. Or if all of my factories say that they make a positive contribution to the energy, then actually the very best the very best solution. So if all these unary factors, those are terms in my energy function, if all of them are non-negative, then the very best assignment I could get would be to simply switch all assignments off. So I would have no tracking whatsoever. The solution, is correct according to this graphical model, but is not very helpful. So making all of these decisions independently would not result in a valid tracking. And we will need some kind of higher order factor in our graphical model. Can you make a suggestion what would be good higher order factors? Excellent. Yeah, so we would have a factor that connects all random variables starting from the same object or ending at the same object. So let's say I would have a factor, I hope you can see that, a green factor connecting these two. And I would have another factor connecting these three here. And then I would have factors for the incoming associations. And there we go. So we have these higher order factors where green encodes that each cell has a unique fate. So the first cell here could only become this one, or could only become that one. And we have these other factors telling us that each cell, well, I'm always saying cell because we work in these biological applications. I could say that each target has just one passed. And these are potentially higher order because, so if you consider this one here, for example, it is connected to 3 variables and it depends on the number of associations have. So if I don't prune by maximum distance, then I would have much higher order factors here. So, and if I want to put this in a formula, then I want to have a potential depending on a clique, where the variables in the clique are those that are connected to this factor here. And if I say that y is the vector collecting all of these binary random variables, then I could say it makes a contribution of 0 to the energy if, when I sum over all random variables in this clique, they sum to 1. So here each target must have exactly one predecessor and each target must have exactly one successor. And otherwise, for a configuration that's taboo, that would make an infinite contribution to the energy. Now, can you imagine how one would deal with appearances or disappearances? I haven't quite understood. So you would introduce some new kind of factor, or what would, or you? Mm-hmm. Okay, so if we say that a cell would be allowed to disappear, then you would give the state that where the sum of the random variables is 0, you wouldn't give it infinite energy, but some kind of finite energy. Yes, that would work. However, we would then still need to enforce consistency, I think. So let's say if we allow this one here to have a finite energy, if all of its associated random variables are 0, so this one would be 0, and this one would be 0, and this one would be 0. Then I would have to make the correspondingly also correct decision on the other side. So the factors on the other side may also need to be modified. And I think your suggestion may work. But the standard procedure to do it is as follows, namely to introduce some kind of meta node where you say here you have a generic node or a generic detection that can explain all appearances, and then a generic one that can explain all disappearances. And these generic nodes are then, so the appearance nodes are connected to all detections at the later time step, and the disappearance node is connected to all detections at the previous node. And one can then introduce additional random variables here and still use the same constraints that I had previously formulated, except that for these new nodes, one would not require that each target has a unique fate, because there could be multiple appearances in principle, or there could be multiple disappearances. So I would not introduce higher order factors for these new appearances. And I should not draw a circle here, because a circle sounds like or looks like this would be a new random variable, but the new random variables are only associated with these. Let me draw a cloud here, because these new random variables are only associated with these artificial associations. And they will also come with unary potentials. So I would have a fixed cost for each appearance or disappearance. Because if I make them too cheap, or if I make them cost no penalty, then I would explain everything just in terms of all variables from t disappeared, and all objects at time t+1 just appeared out of nothing. So I need some fixed cost with these appearances and disappearances. Okay, so we have this graphical model, and we know how to optimize this. It is an undirected graphical model. Because not everything is connected to everything. This is a Markov random field. And we've seen it, we can optimize such problems by writing them as an integer linear program. So in this case here, it would be a minimization of all these unary potentials. So this is the cost of switching association I on, and I only evoke this cost if I truly turn this variable on. So I could probably omit one of these yi's and still be, so I could probably just write it like this. So psi I would be the cost of an association, and yi means that I actually activate it. And now we require that each of these y's is a binary variable. Let's say there are a total of m detections here. And then I have the sums over these cliques of these higher order factors. And I require that they sum up to 1. And I have one clique for each detection. My notation is a bit sloppy for this last part here. So for each detection, I have one clique, and which variables exactly are in this clique comes from this step number 2, where I established all possible associations, or at least almost all. So far, so good. So we can solve this, but only if we know what these unary factors should look like. And structured learning is all about learning the proper form for these unaries from a training set. So given some training set, we can learn the unaries. And we could do this in an unstructured fashion, in an unstructured way, where we would simply get an annotated training set where somebody said that, well, in actual fact, the first object corresponded to the first one, and the second object corresponded to the second one, and the third object corresponded to the third one, we could use such a ground truth and then simply learn a classifier based on the local features that I had listed here. And this is an okay approach, and this is what people have done. However, it ignores the structure in the problem. And if we don't want to ignore the structure in the problem, we're back to today's topic, namely, we can use structured learning. And in particular, we will today look at margin-based or max margin or wide margin structured learning. And the most famous method to do this is the so-called struct SVM.